Among the many moons orbiting Saturn, few seemed less promising for exploration than Enceladus, a tiny icy world only about 500 kilometers across. But appearances can be deceiving. Thanks to the relentless curiosity of the Cassini mission, Enceladus went from obscurity to center stage in the search for extraterrestrial life. It all began with a surprise. As Cassini made repeated flybys of Enceladus, it detected something extraordinary: plumes of icy material erupting from the moon's south polar region. These massive geysers were shooting water vapor, organic molecules, and microscopic ice particles hundreds of kilometers into space, forming a faint yet detectable atmosphere around the moon. Initially, scientists were baffled. How could such a small, cold body generate enough energy to power these eruptions? The answer, it turned out, lay beneath the surface. Cassini's instruments revealed that the geysers originated from fractures in the ice, now famously known as tiger stripes. These fissures weren't just surface cracks, they were the vents of a subsurface ocean of liquid water, kept warm by tidal heating as Enceladus was stretched and compressed by Saturn's immense gravity. This discovery was revolutionary. For decades, scientists believed that life could only emerge in the so-called habitable zone, the narrow band around a star where liquid water could exist on a planet's surface. But Enceladus shattered that assumption. Here was a moon far beyond the sun's warming rays, harboring liquid water beneath an icy shell. Even more incredible, Cassini flew directly through these plumes, not once, but multiple times, and analyzed their contents. What it found changed everything. The plumes contained organic compounds, molecular hydrogen, and microscopic salts, the basic ingredients for life as we know it. The presence of hydrogen was especially important. It suggested hydrothermal activity on the ocean floor, similar to the hydrothermal vents found on Earth's seafloor. These vents are teeming with life, ecosystems thriving in darkness, fueled not by sunlight but by chemical reactions. Could Enceladus be hosting similar ecosystems? Could there be alien microbes swimming in the dark, pressurized depths of its hidden ocean? We don't yet know. But what Cassini revealed is that the conditions for life may be far more common in the universe than we once imagined. It pushed the frontier of astrobiology outward, not just to Mars or Europa, but deep into the cold outer solar system. The images of Enceladus backlit by the sun, with its geysers silhouetted against the blackness of space, became some of the most iconic visuals of the entire mission. They were more than beautiful. They were a beacon, calling humanity to return and explore further. Enceladus transformed from an icy rock into a world of possibilities, and Cassini, once again, had changed how we see the cosmos. As we reflect on this discovery, one thing is clear: we are only at the beginning. Enceladus is waiting, its secrets buried under kilometers of ice. Future missions will no doubt return, armed with more powerful tools, and perhaps, just perhaps, they'll find something swimming in the darkness below. Coming up next on Infinity Beyond, we'll explore Saturn's mighty magnetic field and how Cassini uncovered an invisible force shaping the entire Saturnian system. In the grand cosmic theater of Saturn, most eyes are drawn to the dramatic. Its shimmering rings, its massive storms, its multitude of moons. But behind that spectacle lies a force just as powerful yet invisible to the naked eye: Saturn's magnetic field. And once again, it was Cassini that gave us our first real glimpse into this unseen realm. Unlike Earth, whose magnetic field is tilted in relation to its rotation axis, Saturn's magnetic field is nearly perfectly aligned with its spin. This strange symmetry baffled scientists. Every known theory of how magnetic fields are generated, called dynamo theory, suggested there should be at least some degree of tilt. But Saturn defied the rules. This was more than a curiosity. The tilt of a magnetic field helps scientists determine how fast a planet rotates. On Earth, it's straightforward. On Jupiter, it's measurable. But Saturn? The near-perfect alignment made it nearly impossible to determine the true length of a Saturnian day. Cassini's data helped refine this mystery. It showed that Saturn's rotation rate may not be fixed, but rather fluctuates over time, possibly due to interactions between the planet's atmosphere, rings and magnetosphere. In other words, Saturn's day might be fluid, dynamic, and unlike anything we've seen before. Beyond its unique alignment, Saturn's magnetic field plays a crucial role in shaping its environment. It forms a vast comet-shaped magnetosphere, a region dominated by the planet's magnetic influence, stretching millions of kilometers into space. Within this bubble, charged particles are trapped, funneled, and accelerated along invisible lines of force. Cassini dove deep into this region, recording not just the structure of the magnetic field, but also the behaviors of the particles within it. It discovered magnetic reconnection events, where field lines snapped and reconnected, releasing bursts of energy. It observed auroras dancing near the poles, otherworldly light shows triggered by solar winds slamming into the magnetic bubble. Most intriguingly, Cassini detected that Saturn's rings themselves were electrically active. They interacted with the magnetic field, producing radio emissions and even altering the structure of the field itself. This meant that Saturn's rings weren't just passive. They were actively participating in the planet's electromagnetic life. Even more stunning, Cassini discovered that Enceladus's geysers were feeding material into the magnetosphere, creating a plasma torus, a donut-shaped region of charged particles encircling the planet. This linked the Moon, the rings, and the magnetic field into one interconnected system. The dynamics of Saturn were no longer about isolated features, but a living, breathing network of interactions. And all of this happened far beyond what was once thought possible. When Cassini plunged between Saturn and its rings during its grand finale, it passed through the innermost region of the magnetosphere, providing measurements never before captured. It mapped magnetic anomalies, pinpointed field strength variations, and gave us an intimate portrait of a planetary magnetic system at work. What Cassini found wasn't just a magnetic field. It was a window into the planet's soul. Generated deep within Saturn's metallic hydrogen core, this field may hold the keys to understanding not just Saturn, but all gas giants. It taught us that magnetic fields can be complex, ever-changing, and deeply influential, even in places where traditional models break down. Next on Infinity Beyond, we'll dive into Saturn's legendary ring system, how it formed, what it's made of, and the shocking truth about how long it might last. As the Cassini mission progressed into its final phase, NASA engineers devised what would become one of the boldest maneuvers ever attempted in planetary exploration: the grand finale. The idea? To send Cassini on a series of daring dives through the narrow space between Saturn and its innermost rings, a region no spacecraft had ever entered before. It was risky, uncertain, and utterly thrilling. Each pass brought the spacecraft within just 1,500 miles of Saturn's cloud tops and skimmed just outside the innermost ring. For perspective, that's closer to the planet than any satellite had dared to go. The mission team had to carefully calculate every trajectory, every course correction, because a single misstep could send Cassini crashing into debris or plunging uncontrollably into the planet's dense atmosphere. And yet, it succeeded. Cassini completed 22 dives, each more daring than the last, returning a cascade of new data that fundamentally reshaped our understanding of Saturn's interior, ring dynamics, and even magnetic field behavior. These dives revealed that Saturn's rings are far younger than the planet itself, perhaps just 100 million years old. They are also shockingly thin, and composed primarily of ice particles, ranging in size from grains of sand to house-sized boulders. But more importantly, Cassini was able to measure the gravitational pull of the rings and the planet simultaneously during its dives. This allowed scientists to estimate Saturn's core size, determine the depth of its atmosphere, and gain insights into the planet's unique rotation, something that had puzzled astronomers for decades. One particularly surprising discovery was the lack of a well-defined inner magnetic boundary. Unlike Earth's magnetic field, which has a clear axis, Saturn's seemed strangely aligned with its rotation. This challenged existing models and hinted that something deeper within the planet was at play, perhaps in its metallic hydrogen core or layered atmospheric flows. While orbiting within this forbidden zone, Cassini's instruments also detected microparticles of ring material raining down into the planet's atmosphere, a phenomenon scientists dubbed ring rain. This ongoing interaction suggests that Saturn's rings may be slowly dissipating over time, a revelation that has implications for the lifespan and evolution of ring systems across the solar system. And then came the audio. During one of its closest passes, Cassini recorded plasma waves, oscillations in charged particles that produce eerie, ghost-like sounds. These alien whispers revealed interactions between Saturn's magnetic field and its rings, creating a kind of cosmic symphony that scientists are still analyzing today. The danger was real, but so was the payoff. Every second in that narrow corridor between Saturn and its rings brought humanity closer to understanding not just Saturn, but gas giants as a whole. It was exploration in its purest form, bold, uncertain, and utterly inspiring. The world watched as data streamed back, marveling at crystal-clear images of Saturn's banded atmosphere, turbulent storms, and ring shadows stretching across its surface. It was as though we had touched the edge of the impossible and returned with treasures of knowledge. In the final months, Cassini became more than just a machine. It became an emissary, fearlessly venturing where no spacecraft had gone and delivering insights that no telescope on Earth could match. The grand finale wasn't merely the end of a mission. It was the beginning of a new era in planetary science. Next, on Infinity Beyond, we'll follow Cassini's journey even further, back in time to its incredible launch, its slingshot around Venus, and how this cosmic boomerang turned a dream into history. Before Cassini could begin unraveling the mysteries of Saturn, it had to conquer the most complex part of any mission: getting there. Launched on October 15, 1997, Cassini embarked on one of the most extraordinary interplanetary journeys ever attempted, traveling over 7 billion kilometers through the solar system to reach its final destination. But Cassini didn't take a direct path. That would have required far more fuel than any rocket could carry. Instead, mission engineers used the clever technique known as gravity assist, slingshotting the spacecraft around other planets to gain speed. It's like using the motion of a moving train to give a push to a skateboarder, except it's happening on a cosmic scale. First stop, Venus. In 1998 and again in 1999, Cassini skimmed past the scorching planet, using its gravitational pull to boost speed without burning additional fuel. The maneuver was delicate. Cassini had to pass within thousands of kilometers of Venus's surface, threading the needle between safety and catastrophe. Next, it looped around Earth. In a poetic twist, Cassini returned to its home planet for one last farewell. On August 18, 1999, Earth's gravity flung Cassini toward the outer solar system. From space, it captured breathtaking images of our pale blue world, already becoming a distant memory on its journey. But even then, Cassini wasn't done accelerating. A final slingshot around Jupiter in 2000 pushed it to Saturn-bound velocity. Along the way, the spacecraft took detailed images of Jupiter's Great Red Spot, auroras dancing near the poles, and even its swirling atmospheric bands, offering science a preview of the kinds of wonders it would later observe at Saturn. By the time Cassini reached Saturn in 2004, it had traveled for nearly 7 years. It was a voyage of precision, patience, and perseverance, planned down to the second, with each maneuver calculated years in advance. The whole journey was a testament to the genius of the scientists and engineers who orchestrated it. But Cassini wasn't traveling alone. Tucked inside was the Huygens probe, developed by the European Space Agency. Its mission was to land on Titan, Saturn's enigmatic moon. Cassini would deliver Huygens to Titan's orbit, and from there, a second chapter of exploration would begin, a tale we'll dive into very soon. What's incredible is how this entire journey, from launch to orbit insertion, went almost perfectly. In a domain where small errors can mean total failure, Cassini's voyage was a model of interplanetary navigation. It's no exaggeration to say that before it even arrived at Saturn, Cassini had already made history. The spacecraft endured cosmic radiation, temperature extremes, and sheer vastness, all while hurtling at tens of thousands of kilometers per hour. Its systems remained operational, its instruments stayed calibrated, and its mission clock never missed a beat. And when it finally approached Saturn on July 1, 2004, Cassini performed a daring engine burn to slow down enough to be captured by the planet's gravity. The gamble paid off. The spacecraft entered orbit and sent back its first up-close images of Saturn's majestic rings, and from that moment, the mission truly began. Stay with infinity beyond as we continue Cassini's journey. Next, we'll descend with the Huygens probe onto Titan and witness the first-ever landing on a moon in the outer solar system. On September 15, 2017, the Cassini mission came to a dramatic and emotional end. But this was no failure. It was a planned farewell, a heroic dive into Saturn's atmosphere that marked both the culmination of a 20-year journey and the final act of one of the most successful space missions in human history. By this point, Cassini had rewritten textbooks. It had sent home over 635 gigabytes of data, completed countless orbits, revealed liquid oceans beneath icy moons, and photographed Saturn and its rings from every imaginable angle. But there was one final gift it could give: a direct sample of Saturn's atmosphere, gathered during its last descent. The decision to end the mission this way was not taken lightly. As Cassini's fuel reserves dwindled, NASA faced a dilemma. If left to drift, the spacecraft might eventually crash into Titan or Enceladus, moons that could potentially harbor life. Even the tiniest contamination from Earth microbes would violate planetary protection protocols. So engineers designed a final, controlled descent, a sacrifice to ensure the preservation of these alien worlds. And so, Cassini was commanded to dive. As it plunged into Saturn's upper atmosphere at over 120,000 kilometers per hour, Cassini fought to keep its antenna pointed at Earth. For nearly a minute, it transmitted data back in real time, measuring the atmosphere's composition, density, and magnetic environment. Then slowly, resistance overcame control. The spacecraft began to tumble. Its thrusters strained, correcting for as long as they could. And then, silence. The last signal, received at NASA's Deep Space Network Station in Canberra, Australia, was brief. Just a whisper of telemetry before the spacecraft disintegrated in Saturn's skies, like a shooting star nobody could see. It was the end of a machine, but not the end of its story. Cassini's legacy is vast and permanent. The data it gathered will be studied for decades. Its images have become part of scientific history, public imagination, and even art. It inspired books, lectures, and future missions like Dragonfly to Titan and concepts for Enceladus life hunting probes. And in that final moment, when Cassini gave everything, it reminded us of something profoundly human: our thirst to know the unknown, even when it means letting go. Across the world, scientists, engineers, and enthusiasts watched the final transmission with tears in their eyes. This wasn't just a robotic probe, it was a trusted explorer, a silent partner in discovery. And in its ending, it gave us one final beautiful truth. The universe is waiting for us, but only if we are bold enough to go. Coming up next on Infinity Beyond, we'll reflect on Cassini's enduring legacy, the future missions it inspired, and why this chapter in Saturn's story is just the beginning. On September 15, 2017, the Cassini mission came to a dramatic and emotional end. But this was no failure. It was a planned farewell, a heroic dive into Saturn's atmosphere that marked both the culmination of a 20-year journey and the final act of one of the most successful space missions in human history. By this point, Cassini had rewritten textbooks. It had sent home over 635 gigabytes of data, completed countless orbits, revealed liquid oceans beneath icy moons, and photographed Saturn and its rings from every imaginable angle. But there was one final gift it could give, a direct sample of Saturn's atmosphere gathered during its last descent. The decision to end the mission this way was not taken lightly. As Cassini's fuel reserves dwindled, NASA faced a dilemma. If left to drift, the spacecraft might eventually crash into Titan or Enceladus, moons that could potentially harbor life. Even the tiniest contamination from Earth microbes would violate planetary protection protocols. So engineers designed a final, controlled descent, a sacrifice to ensure the preservation of these alien worlds. And so, Cassini was commanded to dive. As it plunged into Saturn's upper atmosphere at over 120,000 kilometers per hour, Cassini fought to keep its antenna pointed at Earth. For nearly a minute, it transmitted data back in real time, measuring the atmosphere's composition, density, and magnetic environment. Then slowly resistance overcame control. The spacecraft began to tumble. Its thrusters strained, correcting for as long as they could. And then, silence. The last signal, received at NASA's Deep Space Network Station in Canberra, Australia, was brief. Just a whisper of telemetry before the spacecraft disintegrated in Saturn's skies, like a shooting star nobody could see. It was the end of a machine, but not the end of its story. Cassini's legacy is vast and permanent. The data it gathered will be studied for decades. Its images have become part of scientific history, public imagination, and even art. It inspired books, lectures, and future missions like Dragonfly to Titan, and concepts for Enceladus life-hunting probes. And in that final moment, when Cassini gave everything, it reminded us of something profoundly human. Our thirst to know the unknown, even when it means letting go. Across the world, scientists, engineers, and enthusiasts watched the final transmission with tears in their eyes. This wasn't just a robotic probe, it was a trusted explorer, a silent partner in discovery. And in its ending, it gave us one final, beautiful truth. The universe is waiting for us, but only if we are bold enough to go. Coming up next on Infinity Beyond, we'll reflect on Cassini's enduring legacy, the future missions it inspired, and why this chapter in Saturn's story is just the beginning. When it comes to Saturn, it's nearly impossible to capture just how fortunate humanity was to have the Cassini-Huygens mission. While 4 robotic probes have made their way to Saturn over the decades, Cassini-Huygens stands out by a wide margin, both in terms of its scientific impact and the legacy it left behind. This extraordinary mission became the foundation of over 4,000 scientific papers, pushing the boundaries of what we know about Saturn, its rings, and its moons. Among its many achievements, Cassini discovered 6 new moons, some with fascinating compositions that challenge previous assumptions about the formation of celestial bodies. And perhaps just as important, it helped ignite curiosity and awe about the outer solar system in a new generation of scientists and enthusiasts. Imagine traveling 7 billion kilometers across the vast emptiness of space. Cassini did exactly that, enduring the cold silence of interplanetary travel for nearly 2 decades. 13 of those years were spent orbiting Saturn itself, methodically collecting data, sending back images that were at once haunting and beautiful, and recording everything from the planet's massive gravity to its mysterious magnetic field. One of the most astonishing aspects of the mission was the detail with which it explored Saturn's intricate ring system. Long thought to be static and uniform, the rings revealed complex dynamics under Cassini's gaze, ranging from mysterious propeller-like features to rippling waves influenced by nearby moons. In a way, the spacecraft acted like a painter and poet, turning cold cosmic phenomena into compelling stories told through pixels and data packets. The mission wasn't just a technical triumph, it was an emotional journey. As it orbited Saturn, Cassini also flew by some of the planet's moons, including the icy world Enceladus. It discovered plumes of water ice erupting from the moon's south pole, an indication that an ocean may lie beneath the surface, one that could potentially harbor life. This alone was a breakthrough that forever changed the way we look at life beyond Earth. Cassini also gave us unforgettable views of Titan, Saturn's largest moon. Unlike any other moon in the solar system, Titan has a dense atmosphere and weather systems eerily reminiscent of Earth's, except the rivers and lakes are made of liquid methane. The onboard Huygens lander descended through Titan's hazy atmosphere, making it the first and only landing ever accomplished in the outer solar system. It sent back astonishing photos of an alien landscape, rocky, frozen, and dark, but strangely familiar. The mission's end was as poetic as its journey. Rather than letting Cassini drift off and potentially contaminate a moon with Earth microbes, NASA chose a dramatic finale. On September 15, 2017, Cassini made its final plunge into Saturn's atmosphere. It burned up like a meteor, sending back data until the very last moment. That final dive was more than a safe disposal. It was a tribute, a swan song, for one of the most ambitious and enlightening missions in human space history. It reminded us that even machines, when guided by human curiosity and ingenuity, can write stories of exploration that inspire generations. And so, Cassini became not just a spacecraft, but a symbol of humanity's insatiable drive to understand the universe. From its launch to its final breath, it was the eye, the mind, and the heart of our collective journey to Saturn. Stay tuned, because here on Infinity Beyond, we're just getting started. In the next chapter, we'll explore the secrets Cassini uncovered during its daring dives between Saturn and its rings, revealing data never before seen by humankind. As Cassini settled into orbit around Saturn in mid-2004, one of the most historic chapters of the mission was about to unfold. Nestled within the spacecraft was the Huygens probe, built by the European Space Agency. Its target? Titan, Saturn's largest moon, and one of the most Earth-like bodies in the entire solar system. Titan had long fascinated scientists. Shrouded in a dense, nitrogen-rich atmosphere with a surface pressure higher than Earth's, it was mysterious, hazy, and cold, its surface hidden beneath thick clouds of orange smog. But it wasn't just the atmosphere that drew attention. Titan's surface features, lakes, rivers, and possibly rain, suggested active weather systems, though not of water, but liquid methane and ethane. On December 25, 2004, Cassini released the Huygens probe. For 3 weeks, the lander coasted silently toward Titan. And on January 14, 2005, it began its dramatic descent. For over 2 hours, Huygens plunged through Titan's thick atmosphere, deploying a series of parachutes to slow its fall. Instruments aboard measured wind speeds, temperatures, and chemical compositions. It was the first time any spacecraft had attempted such a landing in the outer solar system. The stakes were astronomical. As Huygens descended, its cameras pierced the haze and revealed a world eerily reminiscent of Earth. Dark river valleys, icy highlands, and coastlines that looked carved by liquid flow. But this wasn't water shaping the surface. It was methane, flowing like rivers across a frozen desert. When Huygens finally landed, it bounced softly on what appeared to be a damp, sandy plain. The data confirmed what many had hoped. Titan's surface was solid, complex, and geologically active. It wasn't a lifeless rock, it was a dynamic world, sculpted by alien weather and strange chemistry. For 72 minutes, Huygens transmitted images and readings from the surface, giving humanity its first view from the ground on a moon beyond the asteroid belt. The photos showed rounded pebbles, possibly made of ice, strewn across the landing site. Evidence of erosion, movement, and perhaps even seasonal cycles. What Huygens accomplished was nothing short of revolutionary. It proved that the conditions for complex planetary processes weren't exclusive to Earth. Here, on a frigid moon nearly 1.4 billion kilometers from the Sun, rivers flowed, clouds formed, and rain fell. Titan became the first world in the outer solar system where humanity had stood, even if only through our robotic envoy. Cassini, orbiting high above, served as the communication link, relaying Huygens's data back to Earth. The partnership between the two spacecraft marked a milestone in interplanetary exploration and international cooperation. It was a moment when science transcended borders and united efforts from across the globe. The success of Huygens inspired new dreams. Could Titan harbor microbial life in its subsurface oceans? Could future missions land floating probes on its methane seas? These questions have since driven mission proposals like Dragonfly, a rotorcraft lander set to launch in the 2030s. But none of it would have been possible without Cassini and Huygens paving the way. The images from Titan's surface, of dim sunlight filtering through a thick alien sky, remind us that the universe is not just vast, but richly diverse. Every world has a story, and Titan's is just beginning to be told. Up next on Infinity Beyond, we'll shift our gaze to Saturn's other mysterious moon, Enceladus, and uncover the astonishing discovery that changed the search for extraterrestrial life forever. Cassini wasn't just a spacecraft, it was a marvel of human ingenuity. Built by NASA in collaboration with the European Space Agency, ESA, and the Italian Space Agency, ASI, the Cassini-Huygens mission was one of the most complex interplanetary endeavors ever attempted. Let's go inside the machine that made history. At its core, Cassini stood over 6.8 meters tall, about the size of a school bus standing upright. It weighed more than 20,100 kilograms, and every gram of that mass had a purpose. Packed within its structure were 12 scientific instruments, dozens of subsystems, thrusters, sensors, and the Huygens lander tucked safely on board. But powering Cassini posed a challenge. At Saturn's vast distance from the Sun, solar energy is practically useless. Instead, Cassini relied on 3 radioisotope thermoelectric generators, RTGs, devices that converted the heat from decaying plutonium into electricity. These RTGs quietly powered the spacecraft for more than 2 decades. Cassini was built to endure extremes, cosmic radiation, frigid temperatures, and the vacuum of space. Its structure included protective shielding, thermal blankets, and a robust propulsion system that allowed for complex maneuvers around Saturn and its moons. One of its most iconic features was its large high-gain antenna, which not only relayed data back to Earth across billions of kilometers, but also doubled as a shield during the dangerous ring crossings late in the mission. This antenna transmitted images, magnetic readings, atmospheric samples, and countless bytes of information at rates up to 165,000 bits per second. Remarkable considering the vast distance. Each of Cassini's instruments served a specific purpose. ISS, Imaging Science Subsystem, captured stunning visible light photos of Saturn, its rings and moons. CIRS, Composite Infrared Spectrometer, measured temperature and heat emission across the system. EMAG, Magnetometer, mapped Saturn's magnetic field and detected interactions with the solar wind. INMS, Ion and Neutral Mass Spectrometer, analyzed gases and particles, including the plumes of Enceladus. Radar, penetrated Titan's thick atmosphere to reveal surface structures never before seen. These tools work together to turn Cassini into a robotic scientist, capable of making autonomous decisions, adjusting course mid-mission, and capturing once-in-a-lifetime phenomena. Perhaps most impressively, Cassini was designed decades before modern smartphones even existed. Its computing power was a fraction of what fits in a pocket today, and yet it operated flawlessly across 1 billion kilometers of space, with no room for error. Every command sent to Cassini, each maneuver, photo, and data burst, was programmed hours, sometimes days, in advance. There was no joystick, no real-time control. Engineers on Earth had to anticipate everything, and Cassini had to think for itself when problems arose. This was particularly true during Saturn orbit insertion in 2004 and the grand finale dives in 2017. In both cases, Cassini had to perform critical burns, flip orientations, and execute science programs all without real-time input. And it delivered, spectacularly. Over the course of its mission, Cassini completed 294 orbits, took nearly 500,000 images, made 162 targeted flybys, and changed our understanding of the outer solar system forever. The spacecraft wasn't just a vessel, it was a symbol of collaboration between agencies and nations, of patience from a mission that took 20 years to complete, and of ambition, because Cassini didn't just visit Saturn, it redefined how we explore. Up next on Infinity Beyond, we'll look at the emotional and scientific weight of Cassini's final act, its deliberate dive into Saturn, and the legacy it left behind in its final transmission.